In this video, we want to emphasize linear programming, and in the end, I also want to add the optimization algorithm. Optimization is the way of our life, it's everywhere, and it can be through many kind of questions, which is ask you, can you find optimal results? And many NP-complete, NP-hard problem belong to that group. And last time we said for NP-complete and NP-hard problem, we cannot find the solution in polynomial runtime, but we would like to use some technique to find the solution close to optimal. So today we want to check linear programming and approximation algorithm. Linear programming is one of the ways to perform optimization. And let's take a look at one example. This is a famous traveling salesman problem, TSP. A FedEx deliverman has 6 packages to deliver in a day. The warehouse is located at point A, so the deliverman, the FedEx man, they have to get the package from the warehouse. And since they have 6 packages, and they need to send these 6 packages to 6 houses. And they have a distance between the ending point. They have distance about the cost, the path weight, the cost for deliver packaging from A's position, the warehouse, to the U house, to the or they have the cost from house A, house U to house W. The 6 delivered destinations are given by U, V, W, X, Y, Z, and also the specific paths between the houses. Not every house can reach to another one, but through the path, they can some way to reach to another house. The numbers on the numbers indicate the distance between the houses, right? And to save on fuel and time, the delivery person wants to take the shortest route. So this traveling salesman problem asks the following question. Given list of cities and distances between each pair of cities, what is the shortest possible route that visits each city and returns the original city? This is the original question about this traveling salesman problem. And this is for FedEx delivery problem. It means they adapt to that, and the underlying computation is the same. Delivery person will calculate different routers for going to all the 6 destinations and then come up with the shortest route. And here we want to make sure each specific house they just visit for once, because you want to save your cost, right? In this case, the objective of the delivery person is to deliver the package on time at all 6 destinations. The process of choosing the best route is called operation research. Its approach to make a decision involves the method to operate on system. And linear programming is used to obtain the most optimal solution for a problem with given constraints. In linear programming, we formulate our real-life problem into a mathematical model. It involves an objective function, linear inequalities with subject constraint. And let's take a look at a simple example. Take a look at what is the linear programming model for operation research problems. Consider chocolate manufacturing company which produce only 2 types of chocolate, A and B. Both chocolate requires milk and cocoa only. To manufacture each unit of A and B, following quantities are required. Each unit of A requires a unit of milk and 3 units of chalk. Each unit of B requires 1 unit of milk and 2 units of chalk. The company kitchen has a total of 5 units of milk and 12 units of chalk. On each sale, the company makes a profit of $6 per unit A sold, and $5 per unit B sold. Now the company wishes to maximize its profit. How many units of A and B should it produce respectively? Now let me draw a picture. Let's see here. Yeah, I think this one also, this table is clear enough. And first thing to represent this problem in a tablet. So we have A and B. Yeah, I think I would like to write it down here. Okay, go back to here. And then I go to use this one. Okay, so here we wanted to help the company, right? So we have different requirement, and we have to produce 1 unit of A, we need milk 1 unit, and chalk 3 units. To produce 1 unit of B, we required 1 unit of milk and 2 units of chalk. And the company kitchen only have 5. Total is 5, right? Total we only have smaller than or equal to 5. And the total we have chocolate is smaller than or equal to 12 chalk, right? And for each company, and to sell each unit of this one, 5 is $6 for A, $6 per unit. This is $5 per unit. We will ask you how we can use this specific milk and ingredient and chalk to such that make sure we earn the most, right? So in such a case, it is by intuition or by what you have the calculus study, we say that if we want to maximize, what we generate A is $6 A plus $5 B, right? This is what we want to maximize, but we cannot totally randomly do that because we have a constraint. This is a constraint. And this constraint, we have to formulate as the mathematical function, right? We see that we have A and B corresponding to the number of produced A. So if we have A plus B should be less than 5, right? Because total milk we use is 5, not more than that. You can left something. So the amount of each unit is 1 times 1 and 1 times B, right? So this is 3, let's say 3 times A plus 2 times B should be smaller than or equal to 12. So based on this formula, we say we want to maximize 6A plus 5B subject to A plus B smaller than or equal to 5, 3A plus 2B smaller than or equal to 12. And also A and B should be larger than or equal to 0, right? And if you want to emphasize this is integer, it's integer, right? A and B belong to N. Okay, so this will formulate mathematical linear programming model. Now the question it is solvable or not solvable, right? We can use a graphic method to check that. Okay, so for me, I use graphic method to check that it's also corresponding to different slides later. So we see here, A and B corresponding to the amount of A, amount of B. If you want, you can use X and Y. Is okay, right? You can treat A to be X. And this is corresponding to Y, right? Just label. So now let's see here. We wanted to have A plus B equal to 5. A plus B smaller than or equal to 5. That's the first to emphasize equal to 5, right? So let's emphasize equal to 5, right? This is a line. This is a line. X plus, let's use AB. A plus B equal to 5, this line, right? If it is smaller than or equal to 5, it corresponding to this area, right? This area. Cannot be go to here, can only go to here, this part, right? Okay, now let's take a look. 3A plus 2B. We may need to have a little bit higher here, right? Oh. Right? Okay, so now, 3A plus 2B corresponding to this line. Let's use different color. Let's use this color to represent that. So this is corresponding to this one, right? So 3A plus 2B is smaller than or equal to 12 corresponding to this area. This area, right? This is purple area. And this 1A plus 1B, smaller than or equal to 5, corresponding to, let's use this color to represent, corresponding to this area. And such these are two conditions. These are two conditions. We have to satisfy these two conditions. So finally, this is the area. This area could give us some results, at least satisfying these two conditions. Clear? Now the question is, do we need to scan all the integers here, or they go to outside, right? So only have several, if it's integer, only have several points. And also here, and such that if you want to check 6A plus 2B, you can check each specific integer A and B and to see which one gives you highest number. Another thing it is, since each is the object function, subject function of them integer. And you can see here, so 2A plus 5B corresponding to a group of functions, right? So the group of functions just like this kind of things, right? Group of functions. Let's use another color to represent that. Let's use this one to represent. It could be this, the different, just like that, right? Or this one. It means the intersection maybe change, but the slope is the same, right? Slope is the same. And such that you only need to check each specific point in the intersection between the different lines. In that case, you can get optimal results, right? Okay, so this is for this chocolate problem, and we see we can use a linear programming model to solve the problem, and then use the graphic method to get the results. And let's see what is the common steps. First, we have to identify decision variables, write the objective function, mention the constraints, explicitly state the non-negative constraint. For a problem to be a linear programming problem, the decision variables, objective function, and the constraints all have to be linear functions. If all the three conditions are satisfied, it's called a linear programming problem. A linear program can be solved by multiple methods. Solve a two-variable linear program. A graphic method involves formulating a set of linear inequalities subject to the constraints. Then inequalities are plotted on an xy plane. Once we have plotted all the inequalities on graph, the intersecting regions give us a feasible region. The feasible region explains what all the values our model can take, and it also gives us the optimal solution. This is another example. You can, if you are interested, you can take a look at the slides later, and we just skip that. And then this method can be generalized as the simplex method. Simplex method is one of the most powerful popular methods for linear programming. Simplex method is an iterative procedure for getting the most feasible solution. In this method, we keep transforming the value of basic variables to get the maximum value for the object function. A linear programming function is in its standard form if it seeks to maximize the object function. C equal to C1 x1 plus C2 x2 plus Cn xn. Subject to C20, this should be 1 x1. Okay, just like that. After adding a snack variables s1, s2, sm, and this subject inequality function can be changed to be equality function, and such that this become changed to be the linear algebra problem. Give a graph in this module, in this specific topic, and we emphasize more on how to build the linear programming model. Let's see different examples which you work on, which used for graph problems. Given a graph G equal to VE, find V prime belong to V is the subset of V with minimum number of vertices, such that for each edge UV belong to E, at least one of U and V is in V prime. V prime is called vertex cover. This problem is NP-hard problem. A ratio 2 algorithm exists for vertex cover problem. And let's see this example, right? Vertex cover is a vertex connection C such that each edge contains at least one vertex in C. Corresponding to, we wanted to give a graph, find the minimum number of vertices which cover all the edges, right? For example, in this graph, this green vertices, which are the selected vertices, and which cover all the edges, right? All the edges have been covered. So now we want to select minimum number of vertices, cover all the edges. So what is the objective function? The objective function is we want to find the smaller, minimize the number of selected vertices. Let's say define a decision variable. For each vertex, selected or not selected, we treat it as the Boolean variable, right? So we can define xv. We see here, we can just follow this one. Define xv for each vertex v, take the values. This each variable is 0 to 1. And if it's 0, corresponding to not belong to minimum vertex covering. If it's equal to 1, it means it can be selected. And this is minimize all the selected vertex. And sometimes people also want to check minimum weight. Use the vertex weight to see how do you select the vertex. And the subject function corresponding to for each edge, we need to make sure at least one vertex should be included in this minimum vertex covering. So it means for every edge, xu plus xv should be larger than or equal to 1. The maximum matching problem, and give a graph, we want to find a matching, which is a matching corresponding to a subsequence of edges, such that every vertex is incident to at the most one edge of M, not more than that, incident to at the most one edge of M. It may not cover that, but it needs not more than that. For example, give a graph that could have many matches, right? For example, this is one matching, right? And this is, let's use another color to represent a different matching. And this one corresponding to another matching. So if this edge has been selected, it means either of related another edges will not be selected, because we want to make sure each edge only have every vertex is incident to at the most one edge in this matching. So this really do have many different matchings. For example, if this one, right? If this one, you can select this one, you can select this one, right? And now the question is, we want to find maximum matching. To find the matching M, when there is no sequence of edges selected, we would like the number of selected edges is maximized. And in this case, since we want to select edges, we say then use decision variable xe corresponding to this edge is selected or not selected. We want to maximize that. And the constraint it is for each variable, all the adjacent edges, what they selected should be smaller than or equal to 1. And the clique is a subgraph induced by a vertex set K in which all the vertices are pairwise adjacent. For all the distinct UV, a clique size K allotted as KK. And if we have 3 nodes, this is the 3-node clique. If we have 4 nodes, this is the 4-node clique. Clique corresponding subgraph, which is strongly connected. Every 2 nodes in that graph is connected. This is the clique. An independent site is a vertex set S in which no 2 vertices are adjacent. So, for example, this orange vertex is no 2 nodes are connected, right? It is independent connection. Okay, so here I didn't give you the linear model about independent connection, but you can think about that. Okay, so now let's take a look at the approximation algorithm. And let's use the set covering problem as example. What is a set covering problem? We must select a minimum number of rows size such that the size you have picked contain all the elements that are contained in any of the size in the input. Let's take a look at examples here. You may feel clear. So we say we have each points which stay in the U, and we have different X, Y, Z subconnection. We want to choose specific, we want to decide how can we select the size such that cover all the vertices, all the data points, right? And for example, if you have another one, let's draw here. Okay, let's just say we have data points. We have many data points, right? And we have different, each corresponding to one group, one person, and this person can have a different club. And you have different club. Let's see here. So they could belong to different clubs. So they have different sub-connection. We want to select minimum sites. You want to see how many clubs it combined together and such that it cover everybody, every data points. So you can say they have different combinations, right? If you have n is sub-size, you may have 2 to the power of n combinations, and right? And we say this is not efficient. And one of the way it is, and you can treat, if you have weight on each data point, you use that. If you do not have, you use number 1. And you check the average cost for each data points in each club, and then you want to pick up the highest cost for the for the club, right? For the highest, use greedy algorithm. You select the club which has the highest cost, or the cost is lowest cost, right? Lowest cost. And then you select this one. After, for example, here, right? This club includes more data points. You select this one. And then after that is remaining, we have remaining data points. And you consider the average, the cost for each club which count for the data points has been included. And you select the lowest one. And in this way, you want to cover more vertices. Right? You can use greedy algorithm. And this is true. Finally, first you have all this connection to be 0. And then after that, you select the cost-effective set, which is the smallest cost-effective, and select that. And then after that, you add this one to the new generated, pick up the new connection, and then later you check each club and select the lowest cost, for each club, and you use this way. And this is the proof to say here, this, although it's hard to, give you, it may happen, may not happen, give you optimal results, but the results exactly close to optimal. So with the opportunity and to say it's optimal. I think that's all. This topic is optional. Thank you for your listening.